then we can go into today's lecture. So for this week's seminar talk, we have Drago Plecko from ETH Zurich, and he's working on causal fairness with Elias Barenboim. Drago's research interests lie at the intersection of statistics, causal inference, and applied sciences. In particular, he's interested in methods that can be used for applied problems in both social sciences as well as health sciences. He writes a lot of open source software that support applications in causality. So far, he has worked on fair machine learning as well as explainability, and he delves deeply into problems relating to causality in healthcare. He's currently working on a structural framework for causal fairness analysis along with Elias Barenboim, who's working at Columbia. Elias himself was, of course, a student of Judiapur. This work proposes a framework for causally deciding about questions related to fairness and bias in a data set, and provides a set of criteria for making fair decisions. So without further ado, let me hand it to the speaker. Go ahead.
Thank you. Thank you. Okay. Hi. Good morning, everyone. Thanks for the introduction. So just to, I think I need to update my webpage. I recently actually moved to Columbia Computer Science to work with Elias, and before that I completed my PhD at ETH, as Rahul mentioned. So today I want to talk about causal fairness analysis and some of our recent results on this. And actually we have been teaching this very topic in a set of lectures at Columbia. And there's several weeks of recorded material on this. So in this presentation today, I will not be able to cover all of the results that we have, but those of you who are interested can soon find all of these material lectured at Columbia on our webpage of the lab and on our YouTube channel, so you can have a more detailed view of what's going on. So so I just wanted to share the reference as well, right? So this paper has been put on archive, and it's currently considered in the foundations and trends in machine learning. And also, as you can see here, I have a link to our GitHub pages. So actually, the framework that I'm going to discuss is in a quite a mature state by now. We have been working on it for the last 2 or 3 years. And we have code, we have applications of various kinds. And if you want to use the code, if you want to have a look at how we're doing things, please feel free to visit the GitHub pages and feel free to use the paper as a reference. So that's for the first part that I wanted to say, just as introductory. And I was told that people who are attending the talk today will not necessarily be familiar with what fairness is. So just before I start the formal results of the lecture, I want to say a bit about what fairness actually is and what are the challenges in fairness in AI. So one of the famous examples that originated the discussion on fairness in the recent years is from Broward County, Florida, here in the United States. So as you all know, the AI tools are increasingly powerful, right? And they're used in a broad range of applications and situations. And as it turns out, that these tools can also learn some kind of bias that already exists in the data, and they can even amplify this bias in certain cases, right? So in this case in Broward County, what the algorithm was trying to predict is it tried to predict whether people who are released on parole, if they're released from jail, whether they would commit a crime again, right? And what an independent analysis of this tool, so there was a software tool trying to predict this outcome. What an independent analysis showed is that there was a bias against the African American minority for when this tool was used, right? And this raised the question, if so we're using the various AI tools increasingly, and raise the question on how can we control and how can we make sure that these tools are not doing something that might be societally harmful, right? And the examples here are not just in criminal justice. Here's another one that we took from the media. is about Amazon scrapping a secret recruiting tool that showed bias against women. So basically, Amazon, of course, as all of you know, they need to recruit a lot of people who are software engineers. And as it turns out, the recruiting tool that was sort of displaying ads to possible applicants was displaying most of the ads to men rather than women. And of course, this shows some kind of undesired bias, right? And unsurprisingly, these two examples that I cite are just the beginning of the whole thing. And this bias is not just in sort of decision-making settings, but it's also in videos and images, and of course in NLP applications as well. And here I'm not gonna read out, but recently I think the Chat GPT has received a lot of attention, and unsurprisingly, you can find all kinds of biases against different minority groups in language applications of AI as well. And of course, in the United States, all of this has received a lot of attention, and there have been various testimonies, even in front of the U.S. Congress, about this whole problem and about what can be done, and about how the industry broadly the challenges, right? This sort of tries to give a big picture of what some of the examples in the real world are. And what I want to do today is, and this is just another one with of course lawsuits, which is a very common thing to happen here in the US. So basically, after giving like a rough idea of what kind of problems can arise when you're using AI in the wild, say, what I want to say a bit is about why does causality matter, right? For all of these questions, right? And here I want to cite some parts of the U.S. Constitution, and I want to look at some statements from the Supreme Court. And basically, what you can find in the language that is used in the legal literature and used by the courts in the United States is, you can find that to establish evidence of some kind of discrimination, the plaintiff must prove that the age, in this case, age is considered to be a discriminatory characteristic, or the characteristic the person was discriminated on. They need to prove that the age was a but-for cause for the employer's adverse actions. So I don't want to define what a but-for cause is, but a cause, right? Cause is the word that is used specifically in this sentence, right? So there's some notion of causation that needs to be shown if you're trying to argue some kind of discrimination in courts. And of course, this is not just a single decision. There are many others, and there are many sort of parts of the Constitution and of the decisions of the Supreme Court that use the very same language from different years, right? And of course, it appears in all kinds of forms. And for example, it says that if you want to prove that a statistical disparity exists, the plaintiff cannot point, if the plaintiff also has to point to the defendant's policy or policies causing that disparity, right? So it's not, statistical evidence in itself is not sufficient. You need more to argue that there's actually discrimination going on when the AI tool is used. And of course, this is just another one. So proving a causal connection. And basically, what I want to show with this is that people who are regulating this from the legal standpoint are thinking about these questions in a sort of a causative manner, right? Which is the reason why we are looking at this problem from a causal perspective. Okay, so what is the outline for today? I want to go through some parts of this whole story, and what I want to do is the following, right? So in part one, I want to introduce some of the basic concepts of causal inference and tell you a bit about how we're modeling these problems, and then I want to show you some motivating examples which are related to the ones that we have seen previously. After this, I want to go through the fundamental problem of causal fairness analysis. So I want to give a formal statement, or in this case, actually not super formal, because there's insufficient time to actually go through this super slowly. At Columbia, we have a sequence of about 8 or 9 lectures to cover everything that's going on. But in any case, I can really give, I think, a good idea about what the fundamental challenge is in this whole story. And I, after this, want to talk about a theoretical approach to solving this issue, and I want to show you what the end result is, and I want to quickly give you a hint about how an application of this in practice could look like. Okay, so for each of these parts, I think I would need between 10 and 15 minutes, and I think I was told I can do an hour and 10 minutes. Rahul, is that still okay? We've had a bit of delay, and is it okay that I do hour and 10
yeah,
total?
we'll try to wrap by. Yeah, it's good, but it'll be best if you can just speed up slightly over the original time.
Sounds good. Sounds good. So can you just let me know what is my target time to finish?
Say 40 minutes from now.
How many?
40 minutes.
40. Okay. I'll try to do my best. Okay. So just before I go into this, I want to just give you a feel about what the main parts are of our whole framework. So basically, in throughout, we assume that there's an unobserved reality, which is modeled by the structural causal model, which I'm going to define shortly. And basically, from this observed reality, we collect some data, right? So this is the first part. So we do not have access to the actual causal mechanisms that generate the data that we use for the AI system, but we have access to a data set, right, from this unobserved reality. And on top of the structural causal model, what we're going to do is we're going to apply some modeling, and we're going to leverage some domain knowledge to derive a causal diagram, right? And the idea behind the causal diagram is to encode some kind of qualitative assumptions about the structural causal model that is modeling the underlying reality. And now, based on the SCM, we also want to, based on the existing societal laws and norms, we want to define what it means to discriminate based on the actual mechanism. So in the first instance, we pretend as if the structural causal model is known to us, and we then define discrimination and try to see what discrimination means in this context. And based on this, we want to derive some theoretical fairness measures, which can then be used to measure whether there is discrimination in the data or not. And what these measures should take into account, they should take into account the doctrines and social norms that are regulating this whole process. And of course, in the end, we want to empirically compute these measures from the data. And once you can compute these measures empirically, there are 3 different tasks in fairness that we can solve. And I think this distinction may be helpful to ground the problem. So basically, in the first instance, you can talk about bias detection, which means just trying to quantify whether there is a disparity between different groups in the data, and whether this disparity is sort of causally, sort of how is it causally explained. The second one is about trying to improve upon a current situation that you have observed. So maybe you find that the disparity between groups for an AI predictor is too large, and you want to build a new predictor that is better. And in the third instance, you could be trying to improve things over time, right? So this is more like a reinforcement learning type of setting in which you are trying to control for the disparity over time. Okay, so throughout, I'm gonna yes.
Quick question. Are we assuming the SCM or the graph, causal graph is known?
So we are not assuming at any point that the SCM is known. We are assuming that the causal graph is known, but a specific kind of a causal graph that I'm gonna get into shortly.
Yes. Right. So equivalence class is known, but not the specific causal.
So I will even formally define what kind of equivalence class shortly. Yes. Okay. So here, just to note, I have some pointers here in gray, which represent where the respective figure or theorem can be found in the actual paper that I've shared at the start. So if you want to look it up, I can you can just reference the paper. Okay. So I'm going to quickly go through the basics of causal inference, and I want to define sort of the main elements that are sort of relevant to our framework. So the first one is known as the structural causal model, which is it's just a four tuple, all consisting of the following. So you have a set of endogenous or observed variables labeled V1 to Vn. You also have a set of exogenous or latent or unobserved variables, which you can think of as noise variables. And on top of this, this is somehow the crucial part, is you have the specific functions that determine the values of the variables in VI, right? So for each of the VIs here observed, there's a mechanism that sort of based on some inputs determines the value of this, right? So these FIs here in the slide are the key mechanisms of the structural causal model. And of course, to get some kind of stochastic behavior, what you also need is you need to specify the distribution over the noise variables, right? Over the unobserved or over the exogenous variables U, right? So these are the four elements of the structural causal model, and as I said, this is intended to represent the underlying reality that we don't have access to, and we will assume that we don't have access to either of these elements. So we don't have access to the functions f, and we don't have access to the p of u. What we do know, we know what the observed variables are usually, and we need to model what exogenous variables are doing in a model like this. Okay, so this is the motivation for a structural causal model. And you can find axiomatic characterizations of this in Gales and Pearl in '98, or in the work of Joe Halpern, and recently there's a survey from our lab here at Columbia on the same topic as well. Okay, so how does this work in practice? So there's this distinction between observed and unobserved variables, and how is the SCM, how is the structural causal model evaluated, right? So what happens first is there's this space of units, right? And so all of the instances of the noise variables, of the exogenous noise variables, we refer to them as units. So basically, this is your first sampling from the space of units or the noise variables, and you're picking a specific unit U. And after you have sampled from this space, and you're doing this, if you go to the previous slide, you're doing this from the distribution of P of U, right? So over this space of units in gray, there's a certain distribution, right, across this, according to which you're sampling, right? And once you have fixed this unit, what you're trying to really do is you're trying to evaluate the mechanisms of the structural causal model. And what is interesting, sort of to keep in our mind, that after the noise variables have been fixed in the SCM, the evaluation becomes deterministic, right? So what you're doing is you're taking this unit, you're gonna sort of use the values of the U, and you're going to compute what the values are for the observed variables, right? So you're going to do this in order. You're going to take the mechanism of V1, which is the first observed variable, and you're going to sort of compute its value based on its mechanism F1 and the noise variable U1, and you're just going to continue this process until you have computed all of your observed variables, right? And what you can see here is that this sort of view, which is actually relevant for what's coming later on in the discussion, this sort of view shows you that you can decompose the SCM into the mechanisms part plus the distribution over the noise variables, right? So this gives me the whole SCM, right? So one part is the distribution of the latent, the distribution over the noise space, and the mechanisms. And crucially, after you have sampled the noise, the evaluation of the mechanisms becomes fully deterministic. Okay, so that's that's a view of the structural causal model. But what is really important is that the structural causal model is in practice impossible to get, right? There's no way that someone can come and specify, for example, how people are, I don't know, attaining their scores for university admission or something along these lines, right? So these things are notoriously difficult to specify, and in practice we never want to assume knowledge of the structural causal model, because this sort of encodes, this would sort of be corresponding to knowing everything about the underlying nature of the problem, right? Which is very rarely the case, right? Especially in the settings that it may be possible in physics, and people are trying to recover these, say, structural causal models in physics, but in the type of application that we have in fairness, most often we are not able to do anything like this. So instead, what we want to do is, from the structural causal model, we want to construct some kind of a qualitative assumption. And in this case, I want to talk about causal diagrams, right? And what is a causal diagram, right? So basically, every structural causal model induces a causal diagram G, right? And the graph was going to be represented as a directed acyclic graph, such that so every observed variable vi is going to be a node in this graph, and you're going to have an edge from vi to vj if vi is in the parent set of j, which means that when you're computing the value or evaluating the value of vj, you need to know the value of vi. So in some sense, these arrows encode some kind of possible causal influence, right? So if there's an arrow, it means that vi may be causally affecting vj, right? And another important, oh yes, before I go into the bidirected arrows, here's just an example, right? So here you have the observed variables a, b, c, and d on the right, and the mechanism for the d variable depends on a and b, right? And this would just be shown in this baby graph as with arrows from a and b pointing to d, right? So this is how you would construct a causal diagram. And of course, in the second case, it's just E is just a function of C and the noise, and therefore you would draw an arrow from C to E. Okay. And of course, what we also need to model, and this is sort of in causal inference a big concern, what we need to model unobserved confounding, right? And in our setting, the unobserved confounding is going to be modeled through bidirected edges, and there's a bidirected edge between Vi and Vj if and only if the noise variables corresponding to Vi and Vj, if they share information, right? So what this means, if there's a bidirected between Vi and Vj, it means that their noise terms are not independent, or in other words, that there's some kind of latent confounding between them. And if in this example you think of the D and the E variables sort of depending on the same noise variable, if there's shared information between the noise, this will represent the confounding, which is going to be drawn out as it is in the current figure. Okay, and this is just how you would put everything together in the end to construct a causal graph for something like this. Okay, so this is how the structural causal model induces the causal diagram, and in this work we're going to assume some kind of causal diagram is available to us. Okay, and of course there are other important notions that we need to build on, and these are in particular counterfactuals, right? So we need to be, so in cases of discrimination, we're trying to hypothesize what would have happened if you changed a person's characteristic. For example, if you think that there's discrimination based on gender, you could be asking the causal question of, oh, what would have happened to this person had they not been female but male, or something along these lines, right? And this, in causal inference, this is captured through the notion of a potential response, which is basically trying to say how the outcome Y, which may be some kind of salary, or whether you're admitted or employed for a job or something like this, how it would happen under an intervention, right? So if you went into this causal system and you set the person's protected attribute x to some little x, so for example set the gender value to little x, the question is what would be the new value of y for this same set of units, right? So how would this change of the protected attribute affect the outcome that this person has, right? So this is what the definition of a potential response is trying to capture. And of course, we can also talk about counterfactuals. So, and in counterfactuals, it would just mean that we are looking at what the value of y would have been had we changed something. So in some sense, we can think about first observing someone's gender, and then what counterfactual means, it's we observe, for example, that a person is female, and we are setting their gender to be male, right? So this would be sort of a counterfactual type of question, because you have observed what the actual factual value of x is, but you're asking about a different value of x. Okay, so this is what the notion of counterfactual is trying to capture, and we can sort of, based on the structural causal models, we can sort of define what the counterfactuals are, right? And this is contained in the following definition. So basically, for any kind of quantity, you can, through the SCM, define sort of families of joint probability distributions across different possible counterfactual events, right? So I might be considering what would be the distribution of some variable y under some specific intervention, and here I'm considering y with a subscript x, and indicating an intervention that sets the variable x to a fixed value. But I can have, in this probability distribution, I can have multiple things coming in, right? So I can also look at some other variable z, and I can set in this world, I can set the w value to this little w, right? And the question is, if I want to know the distribution of something like this, how do I compute this distribution? And actually, if you think about how we define the SCM, the SCM gives us sort of this notion. And basically, what we need to look at, we are just looking at all of the units used. So here's the summation, right? If I'm thinking of the units as discrete, it can of course be an integral. So what I'm trying to do is, so each of the units has some probability mass, right, that corresponds to this unit, and each of these events, right, we are wondering, for example, for which of the units this random variable y sub x with the intervention is equal to some fixed value y, right? And what we're doing is we're looking across all of these different clauses in the term. We are looking at which units are compatible with this, right? So the joint distribution is just a collection of units, right? We're just sort of accumulating probability mass across different units, which are compatible with these different possibly counterfactual events. And of course, a special case of this. Yes.
Yeah, quick question here. Like,
Yes.
can I understand, if the SCM is known, the
Yes.
counterfactual distribution can be exactly computed, and
Yes.
otherwise we will not be able to. We have to infer it from from other observations that we make.
Exactly.
Is that right?
So exactly. So I'm just defining this here to sort of have a grounding of what is the type of distribution that we're trying to recover. And in reality, in practice, you're going to have the causal graph, you're going to have observational data, and you'll be trying to infer something about the counterfactual distribution from these two things. And this is the sort of the task of identification that you can be solving. Does that answer the question?
Yeah, thank you.
Okay, so basically, what we will have access to is a special case of this above general counterfactual distribution and this special case is when the subscripts x to z are empty, right? So basically, why is this called the observational distribution? Is if the subscripts x to z are empty, there is no intervention that we're performing, right? So we are just looking at things as they are, or just observing the outside reality, right? And what you can show in that case, the observational distribution can be just defined in this way. So, right, so we're just accumulating in the lower equation, we're just accumulating the probability mass, which is sort of compatible with some specific instance of the variable, right? So this is sort of a simplification of the above equation for this specific case when there are no sort of interventions on this system, right? Okay, so this concludes what the observational and counterfactual distributions are, and from here onwards, I want to build a bit on these notions, and I want to try to give you an idea of how we're trying to approach this problem. Okay, So to do this, I'm gonna go through a couple of fairness examples, and I'm gonna introduce the notion of a standard fairness model, and I'm gonna sort of go through the examples in relatively quickly because I mentioned some of them explicitly. Okay, so the first example, and this dates back even to 1974, is an example in which you have students applying for university admissions, and they choose specific departments to which they wish to apply. And here I'm going to indicate with 0 the science departments, and at 1 with d equals 1 the arts and humanities. And basically what is the protected attribute, or the sort of the concerning characteristic on which you could be discriminated is gender in this case, right? So just for simplicity, binary male and female. And what you can sort of hypothesize, there's some underlying SEM here in the blue area, which is unobserved, right? But what we do know is we can construct sort of we can have a rough idea of what the causal diagram for this setting would look like. So basically, what you can see, your protected attribute X, which is here marked in red, may be influencing how you choose your department. So maybe currently males are more likely to apply to a science department, and of course both of these two characteristics could in the end influence your admission outcome, right? And so this is the type of setting that we're dealing with. On the left, you have this unobserved structural causal model that we were discussing earlier, and on the right, you have the causal diagram, right? Which represents only sort of which variables affect other variables, right? It doesn't really tell us what the actual instances of the structural mechanisms are. And I just wanted to, here in this case, I just wanted to show you a possible instance of a structural causal model. And in our work, we are never assuming the structural causal model, but just to be grounding, you could have X, D, and Y to be some kind of Bernoulli variables. And for example, if you wanted to look at what is called direct discrimination, and this is whether the gender directly influences the admission outcome and not through department choice, right? So it's the direct arrow between X and Y. It would correspond to this coefficient alpha, right? If you look at the mechanism for Y, it would correspond to this coefficient alpha that is next to X. Okay, so this is the first example called from Berkeley admissions from 1974, and of course, what is sort of the whole story in fairness is that you're observing some kind of disparity between the groups, and basically what you see, what the starting point of your analysis is that there's some kind of disparity between the groups, right? So the average outcome for so females applicants are predicted to have a lower probability of admission compared to males, right? And the question for you here is, or for us generally, is does this disparity measured by this total variation measure, which I'm going to call TV from now on, is this disparity enough to conclude that there's some kind of discrimination of female students in the Berkeley admissions? And what I will note here is that what is important really is whether what we have, right, whether which of the two mechanisms how they contribute to this overall disparity. Because what you can see here is just a difference in conditional expectations, but if you look at the graph, there are two causal pathways that can generate this disparity. One of them is this direct type of discrimination, and the other one is the indirect, this type of discrimination in which gender influences your department choice, and the department choice may influence your admission outcome, right? If, say, science departments are admitting a student at higher rates, right? So the key issue here, which we will discuss shortly, is that this measure of just making a difference in conditional expectations is mixing different kinds of causal mechanisms in the whole story. And of course, I want to mention, right, this possible example from criminal justice in which the protected attribute is now race, and race may be causing, due to some kind of bias in policing and so on, it may be causing that the number of prior offenses is different according to your race. And of course, in this case, there's some demographic information such as age, and here we're putting a bidirected arrow between race and age because it's sort of difficult to imagine that age could be causing race causally, or the other way around. So we are not modeling this with a directed arrow, but we are assuming there's some kind of covariations there, or we are assuming that there may be covariations between race and age. And if you look at the specific data set, this actually is the case. And basically here the outcome is whether you're gonna whether you predict that the person is going to commit a crime again once they're released on parole. And here's just a sketch of a possible SCM, right? So it's the graph is very similar. It's just now I have some confounding variables here in this age characteristic, right? But the graph is similar. And yes.
A quick question. So in this particular example, we do want the outcome Y to be influenced by W, but
yes,
not by X or Z. Is that correct?
Yes. So in some sense, yeah. So this is a good question, right? I'm going to get to this. I will defer the question because I'm going to get exactly to this point very shortly. And in some sense, your intuition is correct. For some of the causal pathways, you want them to be active, and for some of them, you do not want them to be active. And we're going to discuss shortly how this is regulated and how we can approach this problem. But a very good question. I think the intuition is exactly how you want to be thinking about this problem. Let me just, before I go into this, I just want to give you the last example, and I don't want to spend too much. And this is sort of, the graph is here just a hypothesis graph. This is not actually the graph that we think is true. It's just sort of for demonstration. So basically, in this case, again, we have gender as the protected attribute, and here I have more mediators, right? I don't have just two mediators, but now not just one, but I have multiple mediators, which are in this case education and employment. And we're sort of interested whether there's a connection between your gender and the salary that you receive, right? And the education and employment are sort of the variables that may be in between on causal pathways, in between gender and salary. And again, there could be a confounding variable in terms of age, right? And so what I wanted to say is, what is sort of the punchline from these three examples is that these three examples have some kind of common structure, and this is what we're going to call the standard fairness model. So basically, what is a lot of these applications fit this mold in which you have a specific protected attribute, and I'm thinking here of one-dimensional characteristic. You have a set of mediators, which is here for me multidimensional. So this W set here you should think of as containing multiple variables, and the Z set as well, the demographic variables can be multiple, and the outcome variable is usually a singleton, right? But if what you can see is that all of the three examples are compatible with this. For example, in the Berkeley, what you just need to show, we need to note that the Z set is, for example, empty. And for example, in the census data set, the latest example that I showed, you just combine the W1 and W2 into the set of mediators, right? So we have this sort of nice graph that holds quite generally, and basically the idea is that this graph is sort of less committal than a standard causal diagram, right? Because what I'm not specifying in the standard fairness model, I'm not specifying the causal relationships, for example, between different elements in the W set, right? So what I don't need to know whether there's an arrow from W1 to W2 or the other way around, or if there's confounding between these guys. I don't care. I just put them in sort of a cluster of the mediators, and this notion is called the cluster diagram in the literature, right? And it's easier to obtain than a fully specified causal diagram for all of the variables. Okay, so from now on, I'm going to assume that there's this notion of a standard fairness model, and I'm going to try now to show you what the tension is in fairness, right? So what is the main issue, right? And in words, we can say that the main issue is how do we explain observed disparities found in the data in terms of the underlying causal mechanisms, right? And here I want to try to illustrate what the fundamental problem of causal fairness is. And basically now I'm recovering this Berkeley example, and I have my possible true SCM below the line, which is unobserved. And here the disparity that we observe is the total variation measure, the difference in conditional expectations is just 14%, right? And basically what you can then see is that, right, because female applicants are 14% likely to be accepted, you want to sort of try and map this to the causal mechanism, and you're asking yourself the question of whether the university is guilty of discrimination, right? That we raised before. And what we want to do now, based on our sort of causal understanding of the phenomenon, we want to see whether this is due to direct discrimination, indirect, or possibly spurious, right? And spurious is the discrimination that is going through the so-called backdoor paths, right? For example, in the standard fairness model, it would be explained by the Z set, right? By the demographic variables, right? And if you look at this in this case, the coefficient next to X for Y is 0, so there's no direct discrimination. The two coefficients from X to D and from D to Y are non-zero, so there is indirect discrimination, and spurious discrimination in this case doesn't exist because there is no, the Z set is empty, right? So we can not have any spurious association between X and Y. And if you had access to this SEM, you would conclude that the university is not guilty of discrimination, right? Well, so that is good, right? But this is assuming the SEM. Well, at the same time, someone else might hypothesize a different SEM, and in this SEM, the coefficients are slightly different, but importantly, the M prime can generate exactly the same data, and it can sort of generate, it can generate exactly the same disparity of 14%, right? But in this graph, in this SEM, which is an alternative hypothesis, what you can see is that the direct effect exists because the coefficient with X is non-zero, and the indirect effect does not exist, right? And what it turns out to your answer would in this case be that, oh, the university is actually guilty of discrimination because the direct effect is present, right? And the indirect effect is not present, right? So the question is, how can we reconcile? Yes.
Sorry, a quick question here. So D here refers to what you were calling W earlier. Is that equivalent?
Yes. D is a mediator, and it's exactly, it corresponds to the W set. Yeah.
All right. Thank you.
Yes. So basically what you can see from this example is that you don't really know how to answer the question, right? Because depending on how you construct the SEM, you would reach a different conclusion, right? So what this shows is that this TV measure, which in this case equals 14%, is not sufficient for us to discuss discrimination, right? And this somehow shows this fundamental tension, right? So this statistical measure is insufficient to give evidence about the underlying causative processes in this environment that generate this disparity, right? And of course, here it's important, and I think Rahul, it goes back to the question that you had, I think, which is really good, is which of these mechanisms are actually okay and which ones are not okay. And here I want to mention two sort of the key legal doctrines of discrimination. The first one is known as disparate treatment, and basically what disparate treatment says is that a similarly situated person who is not a member of the protected class would not have suffered the same fate, right? So basically what this means is that if you are female and say you did not receive a salary increase, the question is whether if you were male and keeping everything else the same, whether that would have affected the salary increase, right? So this doctrine is concerned with, in causal inference, what is in causal inference known as the direct effect, right? And the other thing is the other doctrine is called disparate impact, and basically disparate impact can sort of hold true whenever you have any kind of statistical disparity between groups, or in other words, disparate impact also includes indirect and spurious effects, right? So disparate impact doesn't just look at the direct causal effect, but it also looks at the other causal effects. And here we come to the notion of business necessity, right? Which is very important to answer your previous question. Is what the notion of business necessity says. It allows you to use some variables that are correlated with the outcome because they may be relevant to your company. For example, Google may argue that they have to hire people who have PhDs in computer science, and if that is true, if their business cannot succeed without doing this, and there is currently a difference in the proportion of people who have a PhD in computer science, and maybe it's more shifted towards currently towards males, maybe there is a reason why Google are allowed to use this variable to discriminate on, sorry, not discriminate, but to sort of distinguish people based on this variable, right? So these are the three key notions from the legal standpoint, right? And I just wanted to recap and sort of ground the notions in the same example that we had before. So basically, this difference between the two groups, males and females, can be explained in three different ways, right? So the first one that we discussed is if the salary is based on the gender directly. The second one is if the decisions are made sort of based on education and employment, so which is indicated with this X to W to Y pathway. And the third example is if age or nationality are used to infer the person's gender, right? So basically, there's some kind of association between X and Z, and you're using the Z for deciding Y. This will also result in some kind of spurious association, right? And to relate to the legal doctrines that I mentioned, so here the pathway number 1 would correspond to a typical case of disparate treatment, whereas pathways 1, 2, and 3, and if the disparity here is large, could be evidence for the disparate impact, right? So disparate treatment and disparate impact are sort of two slightly different concepts, right? And disparate impact is a more broad concept, which is trying to include other things beyond just the direct effect. Okay, so this is sort of trying to ground what's going on, and this is I think where we can answer your question exactly, Rahul, is that it's usually up to a legal argument or some kind of regulation that which of these variations you accept, right? So maybe the variations due to education and employment when you're deciding salary are okay, but maybe the variations due to gender and age are actually not okay, right? So this is the type of this is some kind of business necessity argument. There's some kind of discussion that you need to have before you can determine what is sort of okay or not okay. And what is the main thing for us is how do we disentangle the variations within the TV measure, right? So, and how do we sort of distinguish pathways 1, 2, and 3 in this slide within this TV measure quantity? And of course, this just we have some kind of attribution problem here, right? In which we are starting from the TV. On the other hand, we have these different notions of like how discrimination is conceived of legally, and basically we have direct, indirect, and spurious variations contained within this measure that we're starting from, right? And what is this causing? This is causing an issue, right? If you go back to the fundamental problem of causal fairness analysis, this is causing an issue because the TV measure cannot distinguish these three things, right? So what we need to do is we need to develop a framework that can allow us to sort of disentangle direct, indirect, and spurious variations within the TV. Okay. And so to do this, to solve this problem, we introduced yes.
Can I just make a quick announcement for the rest of the attendees? So sorry about the delay. We'll make the recording available to all the participants. So in case someone has to leave because it's 7:30 here, like please go ahead. We'll make the recording available. And if you want to stay on, you can. Sorry about the delay.
So can I no problem. Can I get 15 minutes to conclude, because I think I can cover everything to the end if I have 15 minutes.
Yeah, sure. Please go.
Perfect. Okay, so I want to talk about our theoretical approach to solving this problem, right? So far we were sort of setting up. Now I can sort of say something more bold, and I can introduce some of the ideas that we have, right? So first of all, what I want to introduce, I want to define a quantity which is called a contrast. And what I'm doing is I'm looking at the probability of some variable y if I had some intervention C1, right, which can be an intervention that is concerned with for example, with your gender or your race or something like that. And I have some context, so this is some observed information about the people or a subgroup of the population, E1, and I'm comparing this outcome, the outcome y sub C1 conditional on E1 against y sub C0 conditional on E0, right? And E0 and E1 are observed factual events, and C0 and C1 counterfactual events to which the outcome Y responds, right? So we're comparing, as I said, to reiterate, because this is really important, compares the outcome Y of individuals who coincide with these events E1 and E0 in the factual world, but whose values are possibly contrary to the fact intervened following these interventional clauses C1 and C0. Okay, so this is quite important. And if you think about the total variation measure and the difference in conditional expectations, if you take E1 to just be the X1, so an instance of the protected attribute value, and you take E0 to be X0, and you take C1 and C0 to be empty, you can see that the total variation measure is actually a contrast of a form like this. Okay. So this is the basic notion. And now what is nice about what we can do in this case is we can sort of start decomposing these contrasts, right? And this is sort of the key. These are the key theoretical ideas in our framework. So basically what you could do is you can sort of have a step of sort of subtraction and addition in which you're trying to disentangle within this contrast. You can disentangle the counterfactual and factual sort of contrast. So basically, you're disentangling variations, right? Because with this subtraction and addition or rewriting of this contrast, what I'm now comparing in the left side, I'm comparing Y sub C1 against Y sub C0, which means that I'm looking at the difference which arises from counterfactual C0 versus C1, and I'm conditioning on the same event E1 here, right? This is important. Whereas on the other side, the differences arises from the different observed events E0 and E1, whereas along causal pathways, there's the same intervention C0, right? So with this subtraction addition, I'm disentangling the variations in some sense, right? In this contrast. And what is important in the context of fairness, we are thinking of these events and interventions as having something to do with the protected attribute X, right? Because then they will measure something about fairness, right? And what I want to zoom in quickly into the left side, which is the counterfactual contrast. And so what happens in a counterfactual contrast is sort of can be represented very nicely. So what you can do is, if you have the counterfactual contrast in which you have C0 versus C1 and the conditioning event is the same, what you can do is you can, based on the SCM, you can expand this contrast, and you can have a closer understanding of what is going on in this contrast, right? So you have some kind of unit level difference of Y sub C1 minus Y sub C0, and here importantly, because the unit is specified here, this is sort of a deterministic quantity, right? This difference is deterministic. And basically what you can see is that if you expand this out, what you can see is there's a specific posterior distribution which I'm integrating these unit level differences over, right? So based on the observed events, I for each unit U, I see how much of the probability mass in this observed event this unit takes, and then I'm integrating based on this posterior, right? So it's sort of very nice, because what you can see is that this sort of left part stays the same regardless of the event E, but I can somehow change the event E and get sort of different integrals, right? And what is important, what I will say soon, is we're going to think about different levels of granularity of this event E, right? So this event E might talk about specific subsets of the population, right? So it will allow us to quantify discrimination for different subsets of the population, right? And okay, so this is just what I was saying previously, right? So this is what we're trying to get, and what we will do is we will sort of show, right? And if you go back to the start of the lecture, if you recall, there is this space of units, right? And what we will show is that this posterior on the right can help us start. We can start from the sort of general population, and we can sort of average the quantity, the sort of the discrimination. We can provide discrimination measures across the entire population, and then we can sort of become increasingly more granular and sort of end up at like a unit level, right? So we can talk about even unit level discrimination, right? So for a specific person, right? Okay, so this is the first part, which is the counterfactual contrast, which we're going to use to capture causal variations, so direct and indirect variations. And what you also need theoretically is you need to account for spurious variations, right? In which the difference arises from this observed event E1 versus E0, right? And how does the structural basis expansion look for this contrast? Well, it's very similar. So we have some baseline outcome for a fixed unit U, right, which is now y sub c of this unit U. Again, this is just deterministic, but what you have now is your in the posterior, you have a difference of two different posteriors, which is basically trying to measure how much of the probability mass corresponds to U in event E1 versus how much of it corresponds in the event E0, right? Or in different words, how likely the unit U is to be selected under these different events, right? And importantly, and this is something, yes.
Sorry, quick question. So the
Yes.
counterfactuals in the first part of the expansion, not this one, the previous one, is
Yes.
the change in protected group for different units. So, for example, you're asking the question, will the probability of selection change if I change the unit, the person, individual, from, say, male to female, or some sort of equivalent of that? Is this right?
Are you talking about this expression,
Yeah.
or
I'm asking, what do C1 and C0 refer to here?
So exactly. So C1. So for example, for C1, you can think of as intervening to set your protected attributes to say male, and C0 set it to female, right? So and this would sort of capture the entirety of the causal effect, right? So this
All
is
right. Yeah.
sort of an instance, right, that you could be thinking of. And then with the event E, you can control how many people you're averaging across, basically, how many units you're averaging across, if that makes
Right.
sense. Yeah.
Yes.
And but also what you can do is you can think of more complicated interventions in which you are, for example, trying to only capture the direct effect in this type of expansion. But this is the main idea, basically, right? And this is in contrast to this setting in which, right, I have the difference in the selection, right? This is what is going to generate the spurious, right? The association that is going to, in the standard fairness model, go through the Z set in some sense. Okay, so, and of course, again, we're going to think about these events E as having something to do with X, right? It's important to be able to quantify the difference between the groups. Okay, so how do we put all of this together? So what is the view that we have is we started from this contrast, which could be the total variation measure, for example, for a specific choice of C1 and C0 empty, and X1 for E1 and X0 for E0. What we have done first is we can decompose this into the counterfactual and factual part. And we can sort of, each of these we can expand using the structural basis expansion, right? And what you can see is there's some kind of complementarity between these two sort of expansions, right? Because the first one is going to capture causal effects, and it's going to be integrating these effects across different posterior. And the second one is in charge of capturing the spurious effects, right? So it emits in a completely different form, right? So these two types of contrasts are very different, right? And importantly, what you can see is you can see how the key element of the SCM, the P of U, right, the posterior distributions, how they come in, and you can also see where the mechanisms F, right? So the two key elements of the structural causal model, you can sort of see them explicitly in the expansions that we have. Okay, so now I want to talk about how this relates to the explainability plane. So basically what we have, and if you look at our structural basis decompositions, so we have different levels of granularity for the posterior distribution, right? And at the same time, there are different causal mechanisms that we could be looking into, and our starting point is the TV measure, right? And sort of what you can, as I said, sort of hinted at before, you can sort of start thinking about how you would quantify the direct discrimination across the entire population U. Then if you want to be sort of more specific, you could look at the posterior of U given some fixed value of X, of the protected attribute. So for example, this would quantify the discrimination for the subgroup that has a specific value of the protected attribute. For example, it would quantify the discrimination just for females. Then you could go even more precise, and you could say, I want to look at, for example, age subgroups. So Z is the set of confounders. So I can look at the age subgroup. And of course, I can go even further than this, and I can look at different age and sort of age and education subgroups and so on and so on, right? And at the very end, what you have is you have some kind of notion of discrimination at the unit level, right? And what is sort of important is that this is exactly controlled with these different events E that I was introducing before. And here to capture the second part, right? So the first axis is called the population axis. It tells you which part of the population you're including. The second axis is about how to capture these mechanisms, right? And I think, Rahul, it goes back to your question, is how do we capture these different mechanisms? And basically what we want to say is we want to capture the direct, indirect, and the spurious mechanisms, right? And by choosing different values of C1 and C0, you can be selecting different mechanisms, right? And for sort of seeing the details of how we're choosing these C0s and C1s to capture direct and indirect, I sort of refer you to the paper to see the details of that, right? But sort of our approach is going to be to start, right, with general population, direct, indirect, and spurious effects, sort of move along, become sort of more and more refined, go to the sort of from X, then go to the Z level, and still have this notion of direct, indirect, and spurious, and then go to sort of, I don't know, age and education specific discrimination, and then end at the unit level, which is the very last part, right? The most granular level that we can do, right? And sort of the whole discussion around this with a lot more detail is in section 3.2 and figure 3.2 of the reference I shared. And basically, I just want to recap this intuition, right? So you can start from the entire US population, then move into sort of only, for example, women in the US or something like that, or a racial minority group, but let's say women in the US, which is sort of reflected in this posterior P of U given X. And then you can go to, for example, Z and X subset. So, for example, women in the US below 40 years of age. And then you can become even more precise. You can look at women in the US below 40 years with a college degree. And you can then at the end look at Catherine, who is below 40 years. She has a college degree, but she's sort of a very specific unit, a very specific instance, right? So this is the type of granularity that we can increasingly achieve. And importantly, intuitively, at each of these different levels here, the direct and indirect discrimination, for example, you can distinguish, right? And the sort of the size of the direct discrimination may be changing, or the indirect may be changing across these different levels, right? Maybe women in the US who are below 40 with a college degree are heavily discriminated, whereas in general, women in the US are not discriminated so much, right? Or the other way around, and so on, right? So this sort of uncovers some kind of underlying granularity, right? And this is to relate to the explainability plane. This is the population axis and the mechanism axis, right? That you can think of, right? And basically, okay, so in general, the part in red, the measures were in red can be computed from observational data. I think, Rahul, this answers the question whether we're assuming the SCM. We're never assuming the SCM. So the part in green can in general be computed in practice, and the part in red is much harder to compute. Okay, and this is sort of a leap of faith. I just want to advertise the main result from our paper, which can be found in section 4.3 and theorem 4.9, and it is actually very related to the explainability plane. And what the theorem is saying is that at every level of granularity, sort of the population axis, and every level of the mechanism axis, what you have a specific fairness measure, right? You can write down a mathematical expression that is measuring this causal effect. For example, you can look at, I don't know, X specific causal effect, and then look at the direct effect, for example, only for females, right? And you can see in section 4 you can see the entire detail of how we're constructing these measures in practice. Okay, so this is just something that I want to point you to if you're interested in how this is actually executed and how these measures are obtained. I would point you to this part. And one of the key results, and from that you can read off from this previous fairness map, one of the key results is that you can decompose. You can have an additive decomposition of the total variation measure, right, into the direct effect, which is connected to this legal notion of disparate treatment, and the spurious and the indirect effects, right, which is the which are connected to the notion of disparate impact, right? So the TV measure is decomposed additively into these three parts, and there are many other decomposition results that follow from the fairness map, right? And just as the ending, this is my sort of last slide. I want to show you that why this is sort of important in practice. If you actually go to this census data set that we have discussed, you look that there's a disparity between males and females of even $14,000 a year in average salary. What you can show is that you want to look at how this decomposition of the TV measure looks like, right? So this is something that you may possibly have. But what is key is that if you only look at the TV, you could have a different decomposition, right? So here what you can see is if we just look at the TV, we don't really know which of these two decompositions that I'm showing is the right one, right? And they have very different implications, right? If you look at like the direct effect could be very different. So this sort of illustrates that it's very important how we decompose the TV. So right, so disentangling direct, indirect, and spurious within the TV is very important, right? So the TV alone cannot distinguish causally different settings, right? This is the main punchline of the entire talk. And if you want to reproduce this, you can go to our GitHub pages. Yeah, there's a vignette where you can run our code, you can load the real data, you can play with this, and you can actually compute this in practice. And this is, I think, where I can stop for today. And I can thank you for attending. And I'm actually very happy to take questions. I am personally not in a hurry. It's for you, it's the end of the workday. For me, it's the beginning of the workday. So if there are any questions general about this, or if I can provide any pointers, please let me know.
Yeah, thanks, Drago, for the wonderful talk. I had a question in case this is something related.
Yeah.
So there is TV as a measure of bias that people have proposed, and you're clearly saying that is wrong. And now you're
Yes.
proposing a different measure. Is there any way to independently verify that this is the correct measure? Or do we take that?
Right.
Is there some way of saying, yes, this is the indirect effect and here's the benchmark that this matches, or something like that? Not sure whether the question is clear.
Yes, I'm slightly confused. So just to clarify, so I think what we're showing is that the TV measure captures something, right? But the whole idea is that the TV measure captures everything at once at the same time, right? It captures across every unit and every possible causal mechanism. It captures everything at once, right? So what our view is that what you need to do is you need to have a more granular understanding, right, of this. And what is, I think, one way of nicely capturing this is this decomposition here, right, in which you can sort of pick apart the direct, indirect, and the spurious effects. And now, to answer the question, which of the fairness measures is the right one, it really depends on the sort of the societal and the legal consensus and the regulations for a specific phenomenon, right? For example, for some people, I think often people agree that direct effects should always be zero, right? Because it makes no sense to have the direct effect non-zero. But whether you want to look at the indirect effect or whether you want to look at the spurious effect, this is sort of application specific, right? I can imagine applications in which they say, oh, the indirect effect can be non-zero, but the spurious has to be zero, and they can say the other way around, or they can say that they both need to be zero, and so on. So in some sense, what is our idea is that not to necessarily say that the TV measure is completely wrong, or that people should never ever use this. I think computing this as a first instance, I think, is a useful start, but it's sort of good to know that that there's a lot hiding behind all of this, right? And that you need to disentangle and sort of zoom in on the TV and get a better understanding. And then it really depends on the application to which of these measures you really want to look into, right?
Okay, thank you.
Yeah. Okay.
Maybe we can take questions, and if there's no questions, I'll stop the recording, and then we can continue the discussions informally.
I would have a question, and with which methods would these different decompositions of the total variation be estimated?
How you can estimate them? Right. So there are two. Right. There are two parts. Right. There are two parts. So the first part is about like first you need to do identification, right? And I was sort of trying to hint in one of the slides. So it's here, right? So actually the population level measures, the X specific measures, and the ZX specific, for example, you can estimate if you assume the assumptions in the standard fairness model, right? So based on the standard fairness model assumptions, these things become recoverable, if that makes sense. And how to compute them in practice, what we're actually doing is we have some kind of estimation technique. You can start from something basic like actually doing in practice, we're using some kind of double robustness. So we're using some form of augmented inverse propensity weighting, but we're also doing sample splitting, so it sort of satisfies these double machine learning conditions, right? So you can get some kind of nice statistical guarantees there as well. So, and actually it's implemented in practice, and in GitHub pages, if you go and you look at our software, you can actually plug and play. There are vignettes that allow you to run the code, and of course you can go to the source code and see exactly what is done. And in the paper, I think in the appendix, we describe the estimation in a bit of detail to say what is really going on. But general answer is sort of double machine learning based on some kind of augmented IPW. That's the actual estimator underlying the thing.
Okay, thank you.
Yes.
Okay, if you have no more questions, sorry, go ahead.
No, I'm happy to answer anything else if there are any other questions.
Yeah, if there are no more questions, I think I can stop the recording and we can thank the speaker. Thanks, Drago, for joining us.
No problem. Thanks for inviting me.